So welcome everyone to the first Autoware Safe Autonomy Seminar of 2023. It's my great pleasure to introduce Professor Weisong Shi. He's a professor and the chair of the Department of Computer and Information Sciences at University of Delaware. So I've known Weisong for many years, and he's been a wonderful colleague and a good friend. And he has a tremendous amount of activity and huge amount of energy in running the connected and autonomous research, the CAR laboratory, which he had in in Michigan before coming to University of Delaware. And so Dr. Shi, he is really well known for his work in edge computing, autonomous driving, connected health. In fact, one of his papers on edge computing, vision and challenges, has been cited over 5,400 times. So Dr. Shi is also the chair of the IEEE Computer Society for Special Technology Community on Autonomous Driving Technologies, the ADT, and is on the Strategic Planning Committee, member of Autoware Foundation. He's an IEEE fellow and an ACM distinguished scientist, and he has many more awards and has chaired many conferences. So without much delay, I would like to invite Professor Weisong Shi to talk about all the exciting work he's doing in the University of Delaware CAR Lab. Welcome.
Thank you, Rahul. Thank you for the nice introduction. And it's my great pleasure to be here. And thanks for the Penn Engineering for this opportunity to share with you what we call the vehicle computing vision and challenges. Well, actually, when we first starting this, this kind of thinking about what's important for the, vehicles, and vehicle computing was something, a term that as a computer science, we like it to have studying cloud computing, edge computing, and etc. So that's, as you can see, that is one of the terms. But some of you, if you're working in this area, you might using different terms, but don't really be bothered by the term itself. So I think, I hope by the end of today's talk, hopefully either you already agree with me on this vision, or maybe you've been convinced that, wow, this is something really big is happening right now. So without further ado, I will starting today's talk. Sorry, something wrong on my side. Okay. All right. So basically today's talk, including two parts. The first is I want to explain that what is vehicle computing when, in mind when we so that we can bring everybody on the same page. Back to a couple of years ago when I give this talk, the first one I called why vehicle computing, but I don't think by the 2023 we need to justify why we need this. Actually, it's much better for us to see what is this and how can I contribute to this. And then in the second half, I will talk a little bit about the research activities that at the CAR Lab, where majority of the work has been moving to University of Delaware right now, but I still have a few students back to Wayne State in Michigan. So now first, let's take a look of the landscape today. What happened in the connected autonomous vehicle. As you can see that this era is coming. So when we talk about, in the academia, when we say some era is coming, sometimes the professors are always, optimistic. One of my former students who working in a Volkswagen come back to me and said, wow, you are in many occasions, so you are so enthusiastic about something, but some probably it's not that big. But what I want to say here is the CAV is really coming. As you can see from this sort of screenshot prepared by one of my students, as you can see that almost every single OEMs, by the way, if you are not familiar with OEM, in the auto industry, we always name those big car makers as OEMs, okay, like a Ford, Honda, GM, Volkswagen. So as you can see that pretty much, Europe, China, Asia, Japan, United States, every single OEMs are starting team up with either cloud, different type of cloud providers. Some of them even provide, partner with multiple of them. So the reason is very simple. It's because this market is there. As you can see that by 2027, based on the estimation, the CAV market will be $225 billion. And it's actually contribute about 17% of this, related to this growth, related to the GDP. So similarly, what happened is in the United States alone, about 50% of the vehicles running here, 200 million vehicles will be connected. So this is why everybody right now is talking about the connected vehicle. So to give you an idea that CAV, so what does CAV look like? So I just pick one of the, the platform that our lab have been developed, which is based on the photo fusion. It looks like a regular vehicle, but if I tell you that the price, the cost of this, you were getting a sense about why that the vehicle computing era is coming here. Look at this particular platform. We call it Hydra. The hardware, that means not hardware, I mean the vehicle itself is 2017 for the Fusion. It costs only $20,000. But the whole platform itself, it costs $200,000. So where are the other 90% of the cost goes to? So that is something we need to think about it. And I particularly encourage the PhD students and those researchers thinking about that, because this is where the next things gonna happen. So the sensors, obviously, sensor itself is quite costly at this point. And then that perception algorithms, software. So even before the CAV, Rahul is has been working in the cyber physical system. We know that the vehicle alone has more than 6 million line of code. It's the most complicated. I heard, although I didn't verify that, this one particular vehicle have much more line of code than a space shuttle. This is like the most complicated stuff, which I hope sooner this is going to be changed, because those algorithms, in addition to existing vehicle, you're going to add in more and more stuff. How do I do navigation, object detection, tracking, and etc. Eventually, we need to make a decision, because before the decision was made by drivers. In the future, the decision is made by software. So all these things, as some of you probably heard about the software-defined vehicles, this is just to change the whole, landscape of the OEMs. In many OEMs today, as of 2023, they already have a division called software-defined vehicles. I have 2 part-time PhD students, actually both of them working in the SDV division in their companies. So that is just give you an idea about the big things is changing is here, the algorithm, the software, and etc. Because of the software, then we have to relate it to the cloud platform. Because, for example, how are you going to be updating all the software in the sense called OTA, over the air updating? Because that imagine that today you have a machine learning algorithm running on your vehicle. And then if there's a new model comes in, and which if you're in computer science, you're quite familiar with this, right? So for example, you have V3, V4, V5, and now if people is talking about even have more and more different versions. So how do you maintain the consistency of all the vehicles? Imagine 1 year, Toyota, like 2022, Toyota has sold about 10 million vehicles, and each of them need to be updated continuously software. I don't think any of the OEMs today is ready to take on this kind of tasks. So that's why they have to, although they don't want to, but they have to rely on some cloud companies to help them to maintain this kind of software updating and many things that we're talking about. Because Rahul and I, we were involved on this Autoware Foundation. For example, if Autoware as an operating system running on the vehicles, every single module potentially could be updated. Now, how can you update it? And there's a lot of issue related to safety here. You can't randomly just updating them. So that's why. So this big picture here shows you that the map, and then the model training, the data storage. So where this data collecting from those sensors is going to be stored, and then other sometimes you need a simulation, digital twins, and all these related things will be jumping into this exciting field. So to give you a sense, if you are not working in this space, give you a sense about what are these sensors can do right now. So this I use this picture coming from one of the online that source to show you. You don't need to know it. exactly what this the picture is about, but you can get a sense about in a vehicle today, which you bought from the OEM dealership. They have multiple sensors which have different capabilities. And the other thing I want to share with you is there is always multiple ways to do the same thing. For example, parking. Now, people talking about autonomous parking might be one of the most easiest application you're gonna see sooner. A big city like Philadelphia, go to parking, you wish, right? When you go to a Chinatown, there is very difficult parking there, but you wish you just let the car go to find somewhere. But how do you do the parking? You can using LiDAR, you can using camera, you can using radar. You have multiple things you can do. So that is another challenge faced by the future vehicles, because it's not like traditionally one thing, you have one kind of control. Now, the same function could be implemented very differently. As an infamous, I would say, example is, Tesla, at this point, they still don't use any LiDAR because they think a camera is enough. But obviously, camera is not enough because camera in some better weather and stuff, you will run into some other issues here. If you want to go to level 4 real, autonomous driving here. So that just give you idea about what are these sensors and etc. So those, those sensors are capable sensing a lot of things, for the vehicle. So far I'm talking about all the sensor is only used for the driving alone, but that is just the tip of the whole, iceberg of the whole thing here. So let me pick another example to show you that, for example, for the infrastructure management, in the many developed countries, because the infrastructure has been old, particularly in the US, President Biden just a couple of years ago have this $1 trillion, infrastructure, bill is trying to boost, increase this infrastructure here. But then one of the big things here is in the US, it's not necessary you just build the new infrastructure. It's actually how do you maintain them in a safe way. For example, traditionally, colleagues who work in the civil engineering, they deploy sensors on the bridge highways to monitor their behavior. But what happens is, in many cases, the sensors, because the weather is changing, climate is changing, and then many of the sensors is not functioning very well. So what happened today is, given that most of these vehicles already have those sensors, you can rely on those sensors to do this dynamic, real-time monitoring of the infrastructure. This actually has been starting used for some critical infrastructure these days. And I'm not an expert on this, but my colleagues, we are talking about that. Those real-time monitoring of this bridge infrastructure can help extending the lifetime of this infrastructure significantly. For example, during the better weather, there's a pothole here. This is very important. If you are living in Michigan, before, normally during the morning when I drive to school, I saw a small hole there. But then if nothing happens during the 12 hours, even less than 12 hours on my way back, you can see it's a huge hole. And then you can start to see the cars, the tire getting, flat tire because of this. It's very dangerous. Those are the things you need a real time as early as possible. And plus, you can rely on the sensors on these vehicles and also the computing equipment on the vehicles. They can dynamically calculate what's going on with this infrastructure. So this is going to be revolutionary for the infrastructure health management. And this, as you can see, that before was using a very passive way, but today you can do using crowdsourcing in computer science jargon. Crowdsourcing, you can contribute your vehicle using your sensor, doing some kind of computing. Imagine this is what's going to happen soon. You have your vehicle. If you want to make some money, what you can do is you download an interesting app, like a health manager, for example, for Philadelphia. Then you can download this here, and then you will be using that app, using the sensor on your vehicle, do the computation, contribute back to the city of Philadelphia to help them manage the whole infrastructure, reporting all these events. And those things will be done very easily. Is just install app on your vehicle, not on your phone, and then the vehicle will allow you to make some money. And then obviously the OEM gonna make some money from here as well, because the OEM, because they provide the platform. So imagine that the future vehicle gonna be just like today's smartphone. When you download the app, thinking about what's the business model behind the scenes. So you purchase a app, maybe getting a free, you pay somebody, and then you pay for this app, and then that particular app developer pay 25% to Apple. That's why Apple is number one, on the market cap, because of they're sitting there, they're collecting a lot of, kind of revenue from this. This is exactly going to be the future auto industry, OEMs, where they're going to be survive. So I remember when I first go to GM and give a talk, nobody even believed this. There was laugh at that. Oh, that's not gonna happen. They're still very, that immersed in the way the current business model. But I think today everybody realize that is the future. That the OEM is not going to be relying on the vehicle to make contribute the bigger revenue. To the certain point, they will rely on the software update. They will rely on the third-party apps and running on top of your vehicle to generate the revenue continuously for them. So today, when you purchase a vehicle, it's more like you own a vehicle, you have no relationship with the OEM. In the future is you will be continuously have a relationship with them. So this is just give you an idea about the view. That's why a couple of years ago, so we starting think about that. This is a whole new era is coming. As you can see, we put in 4 layers here. The vehicle, edge, and the cloud is pretty common. Many people believe that is the idea for the, for many of these connected vehicles. But we want to add one more layer here. It's the IoT layer. So the vehicle, imagine that if the vehicle is autonomous driving, let's say you drive you park the vehicle in the parking lot, right, while you are sitting in the office. But so what happens if your vehicle actually can drive around, it can do many other things, for example, for non-medical emergency transportation. This can, the one way can help you to generate some revenue for you. At the same time, it can help the society significantly because today, particularly after the pandemic, people with senior living, the senior independent living facility, and also for the people with disabilities, it's really difficult for them to go to even a regular check in the hospital. So because of run out of the workforce, autonomous vehicle will be perfect for these purposes. That if your vehicle anyway is sitting in the parking lot, is not doing anything, but they can go to the health, go to the auto industry, smart home, even for the police officers, for the body wear camera. Like today, the IoT will be able to talk into the vehicle, and the vehicle as a computing unit to help you to do a lot of computing things. So that is the point here is this kind of 4-tier vehicle computing paradigm, and then you can rely on the sensors, the surrounding environment, and then the computing unit, and etc. And those are the things that a vehicle can contribute significantly to there. So if you are not 100% convinced, at the lower part, I write 2 numbers here. In most of the before in the last century, the vehicle utilization is about 10%. Because imagine you just drive to the office, park it there, come back home, parking in the garage, right? So if we can use this vehicle go to 100%, like day and night, you assume they can quickly charge or can getting this refilled, then they can run almost like 100%. So that's gonna be 9 times, 9 times more utilization. So you don't need this. You don't need so many vehicles. And also, even the city's structure of the future city going to be changed. Today, in many of the cities, you have a lot of parking structures. So you assume all these vehicles are moving. You don't need so many parking structures. So that's why even the future city going to be changed. So that's why we think that this is not just a 5 years change. This is going to be compared with in the last century when Ford have this Model T, the transportation, the car going to replace a horse. Today, those connected autonomous vehicles going to change in the way how we're going to be living in the city, completely significant difference. So that is a vision here is how you're going to be, what are we going to do here? So now let's drill down to, well, assume you buy this idea. So how are computer scientists, we can contribute here? What are the challenges? So here is a data we, in Asia, they always called ICV, intelligent connected vehicles. As I mentioned earlier, those terms doesn't really, don't be bothered by them. Just treat them similarly, okay? they focus more on the intelligence. Some people call the CAV is more focused on the connected, but the idea is they're going to generate a huge amount of data, and the vehicle alone will be contributed about the 17% of the data daily generated on this planet, and we needed to handle them. So here is an old figure estimated by credited to Intel. So each autonomous vehicle going to generate 4 terabytes of data. But as a matter of fact, as the resolution of the LiDAR, the cameras is keeping increasing. Today, one of the vehicle probably go to 35 terabytes of data if they continue running for 24 hours. The energy consumption was a slightly interesting thing here is, you might argue that, well, I don't need this amount of the the power. What happened is, if you consider the most advanced one developed by NVIDIA, the one of them is cost like 500 watts. But that's not the end of the story, because if you want to drive a vehicle on the road for safety purpose, for reliability purposes, you need a redundancy. So for most of these vehicles right now is running in California, they actually have 2 redundant systems. So that's why you need more power than if than we thought in our lab. Okay, to just give an idea. So here are the challenges. Now, one of the challenges obviously is the latency, because imagine that you have so many different type of applications running on top of a vehicle in the future. For the transportation, as I mentioned earlier, in the vehicle computing era, transportation itself, driving, only contribute a small portion of the algorithms there. For example, object detection and etc. But there are many other third-party applications. Imagine you want to download a lot of applications running on your vehicle, and those vehicles need to do a lot of things. For example, detect the signs, detect the temperature, detect the the environmental stuff, and detect potholes. Those are the other applications going to be running on your vehicle. So how do you going to be satisfy those latency requirements from the different type of applications? You have a hard real time, software real time, and some of them is no real time requirements. And then how are you going to be handle this? Because of the time limit, I don't want to go to a very detail on this, but just the idea is those are the computing constrained vehicles. I can share with you one view. A couple of years ago, I exchanged with a general manager from Toyota. They don't even want to put in more than $200 on a particular vehicle on the computing equipment. So that goes to an interesting research problem here is, how can you do all this computing within these constraints in such a price unit? Okay, the unit with such a price is also a constraint. You could have put in a huge server there, like but that is not what's going to be happen on the real vehicle. So, accelerating the inference of this type-sensitive vehicle applications is a very interesting topic. The other one is transmission cost. Many of us sitting in the academia, we don't really thinking too much about this. Everybody talking about, wow, we can collecting all this data, the data from the vehicle. By the way, in most of the traditional vehicle, plus those type of new sensors you putting on the vehicle, there are more than 300 sensors available on the vehicle. So if you consider each of them every 5 seconds, you can do a very quick calculation with how much data needs to be transmitted from the vehicle to the cloud. If you assume this model, so that is in the Ford have a huge organization called the GDIA, Global Data Insights team, that 1,000 people is working on the data analytics, how to discover the values from this data. But today they can't do that anymore, because even one OEM, the number of vehicles, the number of data they're collecting is huge. Give you a little bit of calculation here is, assume that you pay AT&T cellular tower to do these things. You imagine that you have 10 million vehicle. Toyota this last year, one company already have 10 million vehicles. Imagine in the 10 years, they actually have 100 million vehicle for Toyota alone. Now, how much data they need to collect it? Who's going to be paid for this? Ask you and I as an end user to pay this, that's impossible. So we're not going to be willing to pay this money for help them to collecting data. So how do you going to be move this data analytics intelligence, go to the edge, go to the vehicle, and then reduce the traffic, save the cost? That's another big thing for this connected vehicle side. So edge computing will be very helpful. The challenge 3 is what I call Rahul is an expert in the cyber physical system. So I just put in here is cyber physical boundary here is another very important thing we need to consider. So many people, when I talk to, as you probably know, today when the people are working on the vehicle, basically there are two groups of people. The one is the traditional, the manufacturer, or from the auto engineering. So those guys are mostly dealing with the real physical, vehicle. The other group of people is more like us, coming from computer science, IT, that we thought, oh, vehicle is very simple, just writing a for loop, they can make a turn, for example. If I ask you writing a code, for example, you detect somebody in front of you. Now you want to hit the brake, right? In the computer science algorithm or in your code, maybe just 2 lines of code. If something, then do something. That is what we get used to. But do you think you can really just writing this code, gonna be putting into the vehicle, sending to the CAN bus, and then you're gonna building a nice vehicle? The reality is not, because you have to consider that in the physical system, that for example, when you hit the brake, and here is the data a colleague has measured for the different type of vehicle in China. They actually physically measure this. If you're hitting the brake, it's taking 230 milliseconds on Lincoln MKZ. And then on the Hongqi in China, H7 is taking 362 milliseconds. So no matter how much you optimize here, the physical world always have a delay here. So when you consider the real timeliness and all kinds of things, you need to consider the end-to-end, for the predictability for all of these things. So those are the things that are very important for us to consider. In addition to that, the vehicle dynamics, you don't want to sit in a vehicle feel like it's very rough, right? So during the early days, when I get a chance to have a test drive on a couple of autonomous vehicles in different companies, the experience is very bad because this algorithm, when they do this, they're not like human beings. They don't give you enough time to respond. When they detect something, they're gonna either hit the brake immediately, and then you will feel like just like this very kind of a strong action on the human body. So when you design algorithms, you have to consider that the vehicle dynamics, the speed. For example, if you want to make a turn, the algorithm itself needs to consider the current speed and also the turn angle and many things that the vehicle dynamics should be considered when you're doing these things. So that was just to give you an idea that you need the predictability in the full stack on the vehicles. Last year, 2 years ago, one of my PhD students, we wrote a paper on IEEE wireless communication. We argue that for the future vehicles here, you need the computation, communication, and the control call design. We call the 4C here. If you're interested, you can take a look at that paper. So basically, this kind of the requirements goes to the vehicle computing. That goes to the evolution of automotive computing system itself. Today, most of the tradition is a vehicle have about 150 to 200 different ECUs. Each of them controls their own. This is okay for the vehicle, before, if they don't have too much other functionalities. But what the problem is, it's very difficult to deploy some diverse, computing intensive applications, makes them not really scalable, and also can fit in the new needs of the vehicle. So here is what the software defined architecture for the vehicle can look like. So you're going to have a hierarchical here. You have different zones. You have the controls, computings, and then, you still have some ECUs, but most of this will be software controlled things here. Just to give you a rough idea, as you can see that in the future vehicle might have 1 or 2 dedicated, pretty powerful computing units. One of them might be reserved for the driving. The other part will be more on these different other third-party applications running on top of it. For example, battery diagnostics. You need to real-time, you need to collecting data, do the machine learning training, and then understanding the status of your battery, because that is very important for you to improve the lifetime and also the efficiency of the battery. So we have another ongoing NSL project is exactly looking for how to use the driving data to improve the battery lifetime and the failures. So those are the idea eventually that you have an edge server, cloud, and etc. So how this is going to be works. In the edge server here, when we say edge server, it could be multiple places. You could be running on a, at a gas station, could be running a cellular tower, or even on some poles, on the roadside unit. You can do a lot of things, and you're going to have a lot of a variety of the computing unit there, GPUs, FPGAs, and etc. Never assume there is only one computing unit will be everywhere. That is not going to happen. So there is a heterogeneity is another interesting things for us to work on this. So this picture just to show you again about what type of these services going to be running on your vehicle. Safety services obviously is very important. Mobility services is more like self-parking, path planning, and etc. Imagine in the future, all these services is not necessarily provided by the OEM. So you probably haven't thought about this today, but if assume there's some insurance problem, if that policy is ready, so you could buy a vehicle from Tesla, but then you download another autonomous driving app, maybe developed by our group, or you can download another app from Rahul's group if you want to make your car as a racing car. Fine, because the hardware is there, but the driving algorithm is developed by one of the third parties, and you can make your car as a racing car if you want. And then you have multiple choices. Today you want to enjoy the life. You can make the easy ones, but then if you want to have fun, you can make it a racing car here. So those are the things going to be changed. It's going to be easily deployed on the vehicle. But this is a vision. Okay, I don't think today any of the vehicle is ready for you to do that. So and then also some information service, and the last one is the computation, because your vehicle have a pretty going to be powerful machine there. And this can be used to do other purposes. For example, when Philadelphia Eagles going to have this, during the games, you have 80,000 people is sitting in the stadium. And today, during that game, everybody using the phone is share videos, share the exciting moment with the friends in the real time. But the cellular tower is just one cellular tower. Maybe there's a cellular tower in there, not enough to handle this. And many of this process can be done by the vehicle we parked on the parking ground, and this vehicle have a huge computing power there, can be used to do this type of things. That's just to share you the vision. I know that there are some companies already doing this. Mobile, they can just drive a huge computing vehicle parked there to provide the communication, computing, storage, and all kinds of things for you. So this just give you an idea. This is our imagination, the future business model. If you're looking for how the money, the coin sign is going on here is somebody pay the money, service customer, and then each of them, like the Apple, this infrastructure service provider, infrastructure provider, hardware provider, and the vendor, OEMs, eventually even yourself as a customer, you can also getting a portion of this revenue. So to a certain point, the ideal case is you getting a vehicle for free because you don't need to pay vehicle any money. By the end of the vehicle, you drive for 10 years, and also you make a lot of money through your vehicle. So this is something that is what we imagine the vehicle computing era is going to be look like. So there's a lot of challenges down the road. Because of the time, I'm not going to be talking each of this, but as you can see that, for example, for any of this this is a research, here is you need a benchmarking, what's the workload look like, right? Because if you come out a new CPU design, new chip design, you need a workload. And then distributed real-time operating system. This is very important because a vehicle going to be talking to other people. Today, even the real-time on the vehicle alone, Autoware Foundation, Rahul, and a group of the colleagues globally, we are working with the Autoware Foundation, trying to make this right now is on the individual vehicle. My group is more interested on how to make the real-time predictability. But then if you think about the next thing, is going to be a distributed, because the vehicle going to be need to talking to the infrastructure, talking to the other vehicle. How can you make this still and the reliable safety? So that is another kind of interesting topic. Programmability. How are you going to be writing code for this? You assume that there is a platform here. Apple have the SDK, so you can easily develop this app develop. But today, there's no such things available. You can easily writing a code for a vehicle. So real-time runtime supported scheduling energy consumption when the EV is coming in. So electrical vehicle, and then that you save the energy, save the power, heat, many things. Security obviously is another big deal. And if you are, Wharton, at Penn, and if you're in the business school, and in other for the people who are in the business world, this is itself is a very interesting issue. There is no such things available, or we don't know what gonna be look like. That insurance company, and then you have the policy makers and etc. There's quite a few things that needed to be completely changed, in terms of this. So that was the idea. Hopefully, I give you an idea about that the vehicle stuff. So in the next, I will take like 10 minutes here to give you a idea about what our lab is doing. So I'm very happy to answer some questions offline, because today probably we don't have time to answer all these questions. And if you're interested to seeking more collaboration, that we will be very happy to do that. So the car lab, which I back to 2017, that when we think about connected vehicle, autonomous vehicle going to be something. So we I form a car lab at Wayne State with a couple of other colleagues, and then immediately we realized that there is no such a platform available. Although there are some small robots, but they're not really for the autonomous, for the computer science people to look at this. So what we have done is in the last few years, we have designed different type of platforms so that we can support our own research. For example, the Hydro One is an indoor autonomous platform, and I think last year, because of several other universities, they want to use this for research and education. We already shipped. We starting, one of my postdocs, starting a small company. Basically, is if there's an order coming in, so they want to buy one, so we just make one to ship to them. So it's sort of I think 5 other universities using this right now. We also have like a Zebra, which can run it out the door, but what is much more powerful, can host 150 kilogram, on top of that. So this is so allow us to starting the workload, the relationship with energy efficiency and etc. So we also have this Hydra I mentioned earlier. So those are the research platforms, so that we available in the lab. This allow us to contribute, to starting research in here. Then back to 2018. So what we did is immediately, as I mentioned earlier, that how can you writing a code, for a vehicle, if somebody want to working on this. So that's why we come out of this Open VDAP, Open Vehicle Data Analytics Platform. So basically, you have, you encapsulate all this kind of sensors. So we provide a library here called a lib VDAP. So then you can writing a code here, reading a sensor very easily, and then so that you can writing to develop a different type of the, different type of applications on that. So that was the vision. We have this Open VDAP. And then, for example, one of the applications to show you that a vehicle, particularly for the vehicle computing, is Liangke has published this paper in 2018. It's called a Safe Share Ride. The idea is, for example, how you can guarantee the safety of the passengers sitting on the Uber and DD, this type of things. So basically, we leverage the speech recognition, driver behavior detection, which technically you can read the driving behavior data, so that you detect if there is some fighting ongoing, etc., and then you can immediately sending a signal to the police officers in case there is a fighting ongoing there. So all these things, is a possibility, because after you have this Open VDAP and you can reading this and to provide the third-party services. Another one, which is we have been developed working with MIT Lincoln Lab, eventually used by New Jersey Department of Homeland Security, using as a reference architecture. The idea is, when the police officer come out with a body camera, during or while they're working close to the vehicle or to a human, when somebody, so those they can rely on sending back the data to the vehicle, so that the vehicle can continuously monitoring what's the surrounding environment. And a lot of this fatality of the police officer is because when they walk out of the vehicle, the environment is dangerous. Imagine that you have a vehicle can continuously monitor this, and then can remind the police officer that if there's a danger while they are working outside. This has been implemented using our, has been implemented, and we call it auto VAPs. Just to show you some interesting ideas of how the vehicle, can be used for the computing purposes. And most recently, we have developed this vehicle programming interface. So that is the one step to moving on to hopefully we can at least for the academia purposes, so that the other and other researchers, colleagues, they can easily writing a code. For example, I give if you want to writing a code in your classroom, that if the camera detects there's an object, then I want to control the vehicle, make it stop. Right? This concept is very easy. But today, I don't think any of us know how to write a code if I give you a vehicle. So what happened here is we provide this a set of the VPIs, and you can do different data control and algorithm. Now, show you example is using 3 lines of code. You can easily writing that you're reading from the camera, line keeping, and then you can make a change. So to keep the car in the middle of the lens. This is a very high level way so that we can encapsulate the vehicle dynamics. The one I mentioned earlier, from the programmer point of view is you just put in the logic here. Okay, I need to slow down. I need to change the lens and etc. So that was the idea we have been developing. The other things we have been working on is how do we provide this distributed computing platform for the connected vehicles. Imagine that I mentioned that Philadelphia Eagles, Lincoln Financial Field. So those you have some computing requirements. You can rely on the other vehicles to running different models. The reason is because different models, they may have different heterogeneous, different computing power, different the architecture. Some of them might have an FPGA, some of them have a GPU. So you have a model, you have to select the right vehicle to run your stuff. That is the one is going to be the reality. So that was another thing I want to mention here. The other thing is when you do the DNA inference, you have a lot of variations. These variations could be caused by the hardware. So for those of you, if you are not familiar with this, even the same hardware, you purchase, the same model, everything is exactly the same. You purchased them from Intel, for example, the CPU. The maximum variability could go to 16%. This is coming from, there's an NSF expedition project funded to Sandeep Gupta at the UC San Diego. Is variability. Even the hardware are going to have a variability. The machine learning model you're running on the same hardware, there is a lot of variabilities. One of my students has been working on this. You find out that in the real life you have a variability, and then how can you really guarantee that the predictability is a big challenge here? This variability coming from multiple potential places. Read, pre-process, inference, and etc. So that is good to, if you're interested in this paper, you're more than welcome. Just write me an email. So we're happy to share you this paper, because that was still under review. In the last December, that based on this observation of the variabilities, so we come out one of the this is a very simple solution. I wouldn't say that it's very complicated, but the idea is if we know that one of the frame that is not going to be, even you finish them, but it's too late, to make a decision. Then we just throw this frame away. So it's key idea is here. I'm just tell you that we are working on this. So in addition, here is another one we have been working on is because the sensor technology is also continuous improvement. So some of these the camera right now, the makers, they want to put in more computing power on the camera itself, so that they can do more computing before they can start sending the data even in the RAS or the Autoware. The data movement within this within the vehicle is also very has a pretty large latency here. I would say in that way, if you are using RAS, because they're using publisher subscriber based architecture. So there's a trend right now is make this camera also computing ready. So what we have been doing here is a collaboration with the Bell Labs. The idea is, can we starting compress these images as many as possible, and then we can using machine learning algorithm on top of this compressed images. To your surprise is, our human beings, when you compress 10 frames, we're gonna see the blurred there. It's not resoluted. However, machine learning algorithms can can surprisingly, they actually can still detect them in a pretty almost similar accuracy there. So that was the idea. We come out of this, so then we can do quite a few interesting things. We're running on the edge and then on the on the vehicle, and then the edge server. You have different version of the at that time, as you can see, we're using V3 at that time to run this. So I think perfect time. So here is all this work is because of we have this our industry sponsors, collaborators, and partners. So they have been either providing data, providing the equipment, donated equipment, and some of them even just allow us to using their stuff. So right now I want to show you the two pictures. This is a star campus at the University of Delaware. This is where our lab actually is there. And here is a D-Star is one of the infrastructure we are trying to build on our star campus. So you're gonna have this roadside unit going to be deployed on these different intersections, and we're going to have some autonomous shuttle. Well, maybe another autonomous bus is going to be running here on the campus here. So I think I was almost ready to stop here. Summary is, hopefully I convince you the vehicle computing era is coming. There is a lot of opportunities, good opportunity for the researchers or PhD students to identify the topics. So I have two relevant events I want to share with you. The one is, if you are interested in this, so we are organized the first, vehicle computing special issue on the IEEE Internet Computing magazine. Deadline is March 10th. Today, you still have like a few, some time to consider this magazine paper so that you don't need to go to that deep, very deep of these theoretical things. So if you are interested, more than welcome to writing a paper, case study, all kinds of things. So we like that. And another one is the IEEE MOST conference will be happening in Detroit, May 17th to 19th. So that if you are interested, this is the first time, first version of the conference, but we already have people from industry, like the Robert Day from Sophie, from ARM, gonna come here give a keynote, and then we have another senior VP from Stellantis OEM gonna come here talking about that. So we also have a tutorial. And the Autoware gonna have a tutorial there, that one of my colleagues from Japan, so he probably will be coming here, have a tutorial. And then we're gonna have a few demos here. Hopefully that some of you can make it. All right, thank you so much. All these vehicles, all these the papers I mentioned are available, online on our website. So if you are in particularly, if you said you don't want to look at many of the things, here are the two papers that sort of a survey papers you can read. You want to get into this field. Okay, all right. I have still have some time. I can happy to take some questions.
Yes, thank you so much, Weisong. This is an amazing amount of work and very exciting. So I'll open it up for any questions, and I also have some questions of my own, but if anyone in the audience has questions. Yeah, so one question I had was, with this Sophie coming in, and Sophie is one kind of API approach, right? So from there is kind of software defined vehicle at the development time, and then, at the testing time, and then during the lifetime of the vehicle. So could you sort of describe, what do you think is the benefits and the first kind of really the killer app, so to speak, for the development time, and then what would be the more important critical apps during the deployment time using this software defined vehicle architecture?
Okay, that's I will try to answer that, because software defined vehicle, even today, if you're asking 10 people, you might get at least 8 different answers.
Yeah, it's like IoT or some buzzwords like that.
Yeah. So I think but the good news is that we all have the Sophie architecture. Sophie itself is continuously evolving at this point. I talked to Robert Day and also the Sophie guy from back to UK. Here is what I'm thinking. Depend if you really want to explore all the Sophie stuff, then the application should be just like testing in the software world. So you want to go through as much possible, go through their different components. But if you ask me that the way for the that one of these killer application they could demonstrate it here very useful would be the autonomous parking, because autonomous parking I think that probably is the one that most likely will be the easiest and the people willing to take that. The reason is, again, if during the autonomous parking, there's no human beings there. Well, they might be still have it, depending if you are going to a parking structure. But in a valid parking style, then most likely you already get out of there. So let the vehicle just drive on their own. So the safety is a less concern. And I know, for example, in China, they already come out a national sort of a standard for the autonomous parking. So if you want, if a particular OEM you want to sell this function, you have to follow that specification. So the more sort of like a standard now. So that might be a very good application for the people to starting to in the real deployment. But for the testing in the development side, I think that because you are not going to run in the real world, right? You're using this object detection on these things. It's depend on the architecture that which one you really want to go through the VPIs, so that you probably come out a application that can leverage this. I haven't seen. I keep talking to them, asking them do you already have some sort of SDK that we can use? Since I haven't seen the API yet, I don't know what the exactly application can benefit from that. Yeah, but the idea is I hope that they will have a certain number of this, be more focused, rather than you want to cover everything.
That's why I'm trying to figure out like what would be the first few, applications like for, and I think, as you mentioned, autonomous parking seems, it's not very critical and it's in a closed system. So I think just having communication to control the vehicle's drive-by-wire system makes a lot of sense. It is still real time, but it's not in a crowded or cluttered space like that.
Yeah, so that is the one I can see will be a function that people is willing to pay. Eventually, which function you can deploy it depends on the customer. But yeah, it's a parking. I think Philly is a typical places people are gonna love it.
Cool. And now, like looking forward, as you started in University of Delaware, what kind of project are you looking, like any one project you can pick that you're looking to launch over there?
Yeah, for this particular one is now I'm quite interested, again, related to the Autoware part. We really want to understanding the workload that, the workload part of the autonomous, the vehicle, and then how this workload can really impact it goes to the Autoware, for example, the real-timeness, the operating system. So this is hopefully by the end of that, we can somebody can deploy it. It is safe enough, safe enough so they can run it. The one I'm collaborating with the PIX, Alex is also with that company, I guess, that we can, once we get in that platform, so we want to running, to implement this and then deploy it here, and so that we can really can test it. And the good news is I like, I show you the Star Campus here is, the Star Campus is not like a pure campus. So university have spending, the state of Delaware, even the state of Delaware is taking the Star Campus as one of the innovation. It's like a pen innovation, a pen innovation. They use this as a incubator. The university already moved the Office of Innovation here. There are 3 Nasdaq listed companies. Headquarters is already on our Star Campus. Wow. So it's very dynamic and moving. So this way, for example, when we started run this autonomous shuttle, we already have a needs here. The Blue Energy, the company, they said that they want to running a shuttle from the Amtrak station to here. So I think this is a very live environment that we want to do here. So another one, you asked me just pick one. I'm sorry, as an academic faculty, you know that, right? We always like a lot of things. The other thing I want to make this is as a live testing environment, so that we also have a digital twin. I'm working with Amazon right now, is trying to make the digital twin of the whole Star campus ready. So this way, if somebody is running, want to test their algorithm, they can through the AWS, through our we call the Bluebird, through the digital twin, then they can running their stuff on our Star campus without coming here.
Great.
But the traffic and these things, the stuff will be available through this digital twins in that case. Okay.
Yeah, I see the background of the Star campus looks amazing.
Yeah, this is just earlier days. It's just one building, but then we are already building quite a few stuff there. Yeah, next time when you come here, you will see it.
Definitely, I'm looking forward to that. Well, thank you so much, for this overview of so many exciting research. And actually, just to say, personally, I think, I'll follow up with you also on the autonomous valet parking, because I think that's something, and looking forward to doing more collaboration through the Autoware Center.